Welcome to today's video that is going to go through a concept known as angular velocity. I'm going to start out just trying to demonstrate to you what is meant by angular velocity and compare it with what you've probably already worked with, which is what we would know as linear velocity. So for example, if I had an object, let's go down here below, that was rotating around in a circle, like so. If I figure out how fast it's traveling around the outside in meters per second, kilometers per hour, whatever unit I choose, that's what we refer to as linear velocity. And from your studies, and even as much as just grade 10 science, you would have looked at the velocity of an object is the distance it travels divided by the time it takes to cover that distance. So if I could figure out that this point traveled, I'm just going to make up some numbers here, 6 meters, right? That was the distance it traveled out there, and that took, and that took 3 seconds. Well, then the velocity of this particle or object would be the distance it traveled divided by the time it took to go through that, which would be 2 meters per second. Pretty basic concept. Well, the concept I'm going to show you is just as basic, except I'm just going to erase my writing here. Rather than figuring out how fast the object's moving on the outside of the rotation, we're going to figure out how fast the angle is changing at the center of the rotation. So for example, that same thing that I just showed you, let's suppose I said, okay, it's going to start here, and it's going to move over to here, and now we say that it traveled, rather than a distance, we're going to say an angle. And let's suppose I use degrees, and this was, I don't know, I look at it, it looks like it traveled about 90, let's make it 80, something easy. So 80 degrees, and it took for that to happen 4 seconds. Right, so it started here, and it was going fairly slowly. It ended up there, took 4 seconds. The angle it changed, so notice I'm not measuring this distance, I'm measuring this angle. So we now use v with a little a subscript to represent angular velocity. Well, I would take the angle that I rotated through rather than a distance. I'd say, well, I rotated 80 degrees. It took 4 seconds for that to happen. 80 divided by 4 would be 20 degrees per second. So the angular velocity will be measured in either degrees per some time or radians per some time. Typically with things traveling in a circle, just because of the connection between radians and the formula theta equals a over r, we will often be working in radian measure, but nothing says it has to be. So that in a nutshell is what angular velocity is. So let's kind of try and formalize that more here with a formula, which I'm going to give you at the top. So the angular velocity of an object is the angle that it rotates through. It says here in radians. It doesn't necessarily have to be radians, but as I said, typically it's going to be, divided by the time that it takes to rotate through that angle. Don't forget this formula. We're going to need to use this from time to time to either maybe calculate the theta if we need it, or maybe we're going to need to calculate an arc or something. But this formula that we learned earlier on, which is a formula allowing us to calculate an angle in radians, will also have to be used at points in this section. All right, let's go and look at some examples. It says a belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. Find the angular speed of the pulley in radians per second. So to just envision what we got going on here, so we got a pulley, and we've got a belt running around this pulley. Right, so imagine the belt runs around the pulley out this way, and it's making, the belt here has a radius of 6 centimeters, and it's making the wheel, or the pulley, is making 80 revolutions every minute. And the question is, what's the angular speed or angular velocity of that object? Well, I got to figure out some angle that it rotates through and determine how long it takes to do that. Well, if I look at this situation, so as I try and determine an angle here, as I was saying, I look at some different options that I have here. One way to get an angle is you say, well, maybe I can calculate the angle. Well, to calculate an angle, I'd have to know the arc it traveled. I do know the radius, but I don't really know any arc. 80 revolutions doesn't correspond with an arc. However, we should be able to translate a revolution, or 80 revolutions for that matter, because we should know that 1 revolution is equal to, in radians, 2 pi radians. So what I'm going to do is figure out what this angle would be if I made 80 revolutions. Well, it would be 80 revolutions at 2 pi radians every revolution for a total angle of 160 pi radians. So I'm going to use that as my angle of rotation. So angular velocity is the angle that I rotated through, 160 pi radians. Now I have to divide that by the time it took to make that angle. Well, it says here it made that many revolutions in 1 minute. But the question wants my answer in radians per second. So it made 160 pi radians. That took 1 minute, which in seconds would be 60 seconds. So now the angular velocity is just going to be 160. Get my calculator going here. 160. Let's see what I'm doing. 160. Multiply that by pi. And then divide that by 60 seconds. And I end up with 8.378. 8.378, and that would be measured in radians per second, which is exactly what they asked me to figure out. Now, here's our second example. This says an ant sits on a CD at a distance of 17 centimeters from the center. If it sits there for 42 seconds, it travels a total distance of 913 centimeters. So if you can imagine what's going on here, we've got a CD. So let's suppose the ant's sitting, we'll say it's out near the edge, and it tells us the distance here is 17 centimeters. So that would be the radius of the rotation as the CD spins. And it sits there for 42 seconds, and it travels a total distance of 913 centimeters. All right, so let's see if we can answer these questions. What angle has the ant turned through in radians? So it wants me to calculate theta. Well, theta is found if you know the arc traveled, which is distance around the outside, and you can divide it by the radius, you will have an angle in radians. So theta equals the arc, which is so it said it travels a total distance of 913. That means it spun around the outside, 913 centimeters, and the radius of the rotation that the ant was making was 17 centimeters. So if I divide that out, 913, and I divide that by 17, I get 53.706 radians. There's part A, done. what speed has the ant been traveling at? Okay, so this is talking about not the speed at the center, it's talking about how fast has the ant been spinning around in the circle, so the linear velocity on the outside. So this velocity is the distance the ant traveled divided by how long it took to travel that distance. Well, the distance it traveled was 913 centimeters, and the time it took, or that they monitored that, was for 42 seconds. 42 seconds. So the speed of the ant would be 913. 913 divided by 42. 21.738 centimeters per second. 21.738 centimeters per second. That's part B. What angular velocity has the ant been spinning at? So now, rather than get the speed it was spinning on out here, what was the rate of change of the angle in here? That's the angular velocity. All right, now we've done all the legwork here for it, so it should be fairly easy to do this. So the angular velocity, we already figured out the angle that it spun through. It spun through this angle, 53.706 radians. And then you say, well, how long did it take for that to happen? It did that in 42 seconds. So 42 seconds. So the angular velocity would be 53.706. Divide that by 42 seconds, and we would get 1.279 radians per second. That's that one. Part D, what RPMs? RPMs is an acronym or abbreviation for revolutions or rotations per minute, is the CD turning at? Well, to get to RPMs, I gotta know one important fact. I need to know that there's 2 pi radians in one revolution. Okay, so that's really important. So what I need to do is figure out what angle did this ant or the CD spin through in 1 minute, because I want revolutions per minute. So let's see here. In 1 minute, the angle would have been so it's 1.279 radians every 1 second. That's the angle that it's spinning through. Well, let's just multiply that by 60 seconds. That's a minute. And we should now have the angle that it rotated through after 1 minute. So we'll take that number, multiply by 60, and I get 76.723. 76.723. That would be in radians. So what you want to now figure out, because it doesn't say radians per minute, I already know that, or I have radians per second. It wants revolutions. So what I want to figure out is, how many revolutions is this then? So how many full revolutions? Because that's the angle it rotated through in 1 minute. So that's my per minute. Take your angle, 76.723 radians, and just see how many full rotations would be made in that time frame. And I know that in one full rotation, there's 2 pi radians. So this is going to give me the number of rotations, full rotations. So if I took that number now, and I divide by 2 pi, I will get 12.211 rotations. 12.211 revolutions. And that would be the revolutions in the time it took to make this angle, which was 1 minute, which is perfect. That's what I'm looking for. So therefore, it's spinning at 12.211 RPMs, revolutions per minute. That's a nice example because it kind of goes through a lot of the different aspects of what I want you to get out of this section. All right, so that's a good one to use as a guide. Let's see what I've got here. Another one with RPMs. All right, so I've got an electric motor. It's turning at 2200 RPMs, and I would like to figure out the angular velocity in radians per second. So to do that, let's figure out an angle. Remember, RPMs, one revolution is 2 pi radians. So 2200 RPMs, 2200 RPMs, just figure out what that would be in radians. So multiply it by 2 pi because you rotate 2 pi radians every rotation. And that would give us 4,400 pi radians. That's the angle that I rotated through. To get the angular velocity, you take the angle you rotated through, 4,400 pi, that's in radians now, and you divide it by how long it took for that to happen. Now it stipulated it wanted us to be in seconds. Well, because that was RPMs, which means per minute, this was the angle after 1 minute. So then just divide this by 60 seconds, like the last one we just did. The one before that, I guess. So now we'll figure out this one, 4,400 pi. Divide that by 60. And I get 230.383. 230.383 radians every second. Now when you think about that, that's something spinning very, very fast, because in 1 minute it's spinning 2200 revolutions. So this is saying that in 1 second it's rotating through that many radians. Remember this, that 2 pi, which is approximately 6.28 radians, that's a full turn, 360 degrees. So this number is significantly larger than that. So it's spinning, making multiple revolutions every second. And if you want to say, well, how many is it doing? Just take this number and divide it by 2 pi. So if I took my answer and divide by 2 pi, because that's how many radians are in a full turn, this motor is making 36.666 revolutions every single second. That's fast. Find the distance a point that is 0.8 centimeters from the center of the rotation travels in 0.008 seconds. Well, let me see here. Just move this down a bit. So we are dealing with a point that is 0.8 centimeters from the center of the rotation. So this is spinning. This is kind of looking at the end of, let's say this is, I don't know if you've seen little electric motors on as kids, you would put a little piece of paper or something on it and you'd put a battery on the end of it and turn it on, it would spin. Well, again, this one's spinning really fast. So we want to figure out how far, what distance, so that's the distance out here. Does that ring a bell with anything? They're looking for you to find an arc, a distance on the outside traveled. So it didn't come out and say find the arc, but that's what they are indirectly asking us to find. The only formula that we have that finds arc is this one right here. This is part B. So to calculate an arc, what I'm going to need is the angle that I rotated through and the radius, which I do know the radius, that's given, 0.8 centimeters. So I got to do one small calculation. In 0.008 of a second, I want to know what angle did I spin through. Well, I know that I go this many radians every second. So in 0.008 of a second, theta should be your velocity, 230.383 radians per second, multiplied by your time, 8 seconds, and that should give you, so 230.383, multiply that by 0.008, 1.843 radians. That's the angle that was generated after that amount of time. So this would be in radians, because it was traveling at that speed for that length of time. There's my angle in radians. And again, I find as soon as you put radians in here, for whatever reason, it'll throw students off. But it's nothing more complicated than this. For example, if I said to you, a wheel is spinning at 2 meters per second, how far would a point on the outside of the wheel travel after 5 seconds? You'd say, well, that's easy. 2 meters per second for 5 seconds? Nothing to it. 10 meters. Well, it's the exact same thing as this. That many radians per second for that many seconds, there's the angle that it spun through. So I now have the angle, and I know the radius. I fill those in. So 1.843 radians equals what I'm trying to find, the arc, the distance on the outside, given a radius of 0.8 centimeters. So my arc is going to be this number times 0.8, giving me a distance of 1.474 centimeters. That would be the distance traveled on the outside of the rotation. Okay, this one is referring to a Ferris wheel. And it says a Ferris wheel rotates 3 times every minute. The passengers sit in seats that are 5 meters from the center of the wheel. What's the angular velocity of the wheel in radians per second? What distance do passengers travel in 6.5 seconds? Alright, so this is fairly similar actually to the last one that we just did, except it doesn't start in RPMs. It gives us, well, I guess it sort of does, because it just says the wheel rotates 3 rotations every 1 minute. So what you want to do is turn that into an angle. Well, 1 rotation is 2 pi, so this would have to be 3 multiplied by 2 pi, which would be 6 pi radians. So to get your angular velocity, you take the angle that you spun through, so 6 pi radians, and you divide that by how long it took to make that angle. Again, same, because it was revolutions in a minute, you would divide that by 60 seconds. So my angular velocity, this one I think I might just even leave it exact. I'll just say it's pi over 10 radians per second. This is now saying if you got your Ferris wheel, and the passengers are sitting 5 meters from the center, so this is the radius, how far do they travel in 6.5 seconds? Well, the distance they travel is on the outside of the circle. It's asking us again to find the arc. To find the arc, you need to use this formula. Theta is the arc divided by the radius. What I need to figure out then is what is theta. I know the radius, it's 5 meters. I just need to figure out the angle that it's going to be going through in 6.5 seconds. So get your angular velocity, and to get your theta, you're going to take pi over 10 radians per second. You're going to multiply it by your time, which is 6.5 seconds. So I'm actually going to throw this all in the calculator here and get an angle. So the angle is going to be pi over 10, and then multiply that by 6.5, giving me an angle of 2.042 radians. 2.042 radians. So that's the angle that it would rotate through in a 6.5 second time frame. So take your angle and put it in here, 2.042 radians. Given an arc, which I don't know, distance on the outside, I'm trying to figure that out, if the radius of the rotation is 5 meters. So the arc will be that number times 5. 10.210 when we are in meters. 10.210 meters. That would be the distance the passengers would travel because they're traveling around the outside of the circle. So their arc or their distance travel would be 10.210 meters in 6.5 seconds. All right, I think this is our last one. And this is where they give you the linear velocity. So this time they're not giving us RPMs or rotations. They're giving us the linear velocity. So it's talking about a bicycle wheel. Here's our bicycle wheel. I know that it has a radius of 36 centimeters. And on the outside, it's spinning, rotating, whichever direction, doesn't matter, at 4.8 meters every second. So determine the angular velocity of this wheel. So the angular velocity is the angle it spins through divided by the time. So unfortunately, I do not have an angle right now, so I'm going to have to come up with an angle. Now, personally, I think the easiest thing to do is this. Let's say you started here, and you come down here and said, you know what, I just traveled 4.8 meters because I know it's going that many meters. So now your arm that was here would now end up over here. So let's imagine you had like a spoke on a wheel. You follow that spoke for 1 second. Now, of course, 4.8 meters is going to be a bunch of turns here, but I just want you to be able to envision this. And we're going to try and calculate the angle it spun through. Well, look at what we know. We know the arc, and we know the radius. Conveniently, we have a formula that allows us to calculate the angle in radians. Take the arc, which is the distance it travels on the outside, divide it by the radius. I'm going to watch units here. 36 centimeters, that's 0.36 of a meter. So now I'm going to take 4.8, and I'm going to divide that by 0.36, and giving me 13.3 repeating, so 13.333, that would be radians. Now, that's the angle it rotated through when it made a 4.8 meter arc on the outside. Well, the time it would take for that to happen, there's your time, 1 second. So when you go to this formula, you put your angle in, 13.333 radians, divide by how long it took for that arc to be made or that angle to be made. Well, that would be in 1 second. So my time here is 1 second. I'm done. That's my answer. 13.333 radians every second. So I've seen students do the same question where instead of using 4.8, someone else might say, oh, I'm going to use 48 meters as the arc. No problem. 48 meters out here. It would be a decent one to use, but here would be the only difference. You would calculate theta. It'd be 10 times this because I'm going to be that. But then when you go over here to do your angular velocity, 48 meters, you say, well, how long would it take to make that arc? If it's going 4.8 meters every 1 second to go 48 meters, your time would have to be 10 seconds instead. Now, I'm not suggesting that this is what I would do because it's a little more confusing. It's easier to just do it in a 1 second interval and get the arc and the radius and your theta for that. But in theory, you could, as long as you pick some time frame, I'm using 10 seconds, is easy enough too. 48 meters divided by the radius, get your angle. Put that angle here, divide it by, instead of 1 second, you'd put 10 seconds. It's going to give you the same answer, 13.333 radians per second. So when you're given the linear velocity and you know the radius of the rotation, it's still relatively easy to get your angular velocity. You just got to calculate your angle first. using our theta equals a over r formula. And that's it. That's all that this unit involves. It's basically introducing you to this new formula that you see right here, and then kind of seeing how it can be tied together with this formula here, and the two of these work together to calculate what is known as the angular velocity. And again, make sure you understand the difference between, your 4.8 meters per second, that's how fast it's spinning on the outside, called linear velocity. This number is the rate at which the angle is spinning or changing at the center of the rotation as it's moving. So there's two different velocities, linear and angular at the center. And our focus was on, in this video, how to calculate and work with the angular velocity. All right, thanks for watching. As always, if you have any questions or problems, reach out, and I'll do the best I can to get you pointed in the right direction. Thanks for watching.